Hello and welcome. In this video, we're going to continue to take a look at series and figure out when they converge or when they diverge. And in this case, we're going to be taking a look at a couple different kinds of tests that we can use in various different scenarios. First kind of test that we'll be looking at is, well, if we have two consecutive terms, let's take a look at their ratio and see if that ratio is getting small enough that it should converge. Unsurprisingly, it's called the ratio test. And another test that we'll be looking at is the root test. And unsurprisingly there, it involves roots and seeing whether or not the root of each term continues to get small enough to converge. Now we're going to be looking specifically at absolute convergence here. So remember in a previous video on alternating series, we took a look at what absolute convergence is. But maybe let's just have a little refresher here. A series is absolutely convergent if the series of absolute values is convergent. So we'll just take each term, an, take its absolute value, add all those together. And if that series is convergent, then we say it's absolutely convergent. And we also have a theorem that's very handy for these particular tests that says if a series is absolutely convergent, then it is convergent. Essentially just think that being absolutely convergent is actually tougher. Having only positive terms added together and still be convergent is a little bit more tricky than having a combination of maybe alternating positive and negative terms. We saw that with the alternating harmonic series. That is convergent, but the harmonic series that is non-alternating is divergent. So we actually say the alternating harmonic series is conditionally convergent. Okay, so we've got the ratio test and the root test, and they test for absolute convergence. Let's start with the ratio test. The ratio test looks at a ratio of two consecutive terms. So we'll pick an arbitrary term, an, and the term after that would be an plus 1. And we'll look at the ratio of an plus 1 over an and hope that it's quite small. If the limit exists and it equals some number L, and that value is less than 1, then the series is absolutely convergent, which also implies that it's convergent. However, if that ratio is some value L that is larger than 1, or if that limit of the ratio goes to infinity, then they're not getting small enough quickly enough to be convergent. It is divergent in that case. And unfortunately, there are scenarios where the ratio test is inconclusive. If we take the ratio an plus 1 over an, take its absolute value, and look at the limit as n goes to infinity, if that equals 1, then unfortunately we can't really conclude anything with the ratio test. This test is going to be very, very useful where the ratio of two consecutive terms can be simplified down to a simple expression. It's really good with powers and exponential functions, for instance. There's one other test that we'll look at in this video. It's a little bit more niche. It really is only applicable in a few circumstances, and that's the root test. Now, the root test also is testing for absolute convergence. In this case, what we do is we look at the nth term in the series, an. We take its absolute value to make sure it's just positive. That would be forming the absolute value series. But we're going to be looking at the nth root of the absolute value of an. And now we're taking the limit as n goes to infinity. So we're taking a higher powered root of higher level terms in the series. If that limit exists and it's less than 1, then it's absolutely convergent. If the limit exists but is greater than 1, or if this limit approaches infinity, then we have a divergent series. And unfortunately, once again, even sometimes the root test is not going to give you an answer. If this limit equals 1, then we have no conclusion. All right, let's try a few examples and let's see if we can maybe use the ratio test or the root test instead of some of our other tests that we've taken a look at to help simplify this test for convergence a bit more. Now, in these examples, we're going to be just testing to see if the series converges or diverges. Unfortunately, these convergence tests don't give us the actual sum, unfortunately. So we'll have to leave that alone, but let's see whether or not this might be a finite series. Now, right away, what we're given here is the expression for an. We actually see that that must be alternating. -1 to the n minus 1 shows up there. So that's actually an alternating series, and we might be able to use the alternating series test. But we also see nice expressions such as powers, n to the fifth, and exponentials, 2 to the n, well, this might actually work out really well if we take a look at the next term up and look at the ratio between the two of them. So let's look at an plus 1. We get an plus 1 by changing all of the n's to n plus 1s. That means that when we have n minus 1, changing n to n plus 1, that will simplify to get us just the exponent n. You can think about that, it's n plus 1 minus 1. So that just gets us negative 1 to the n. And instead of n to the fifth, we have the next term would be n plus 1 to the fifth power. And instead of 2 to the n, our next term would be 2 to the n plus 1 more. Let's take a look at the ratio of an plus 1 over an. And don't forget, we also have to take the absolute value and the limit as n goes to infinity. When we see a ratio of two fractional expressions like this, though, it might be better to actually just multiply by the reciprocal. Rather than an plus 1 over an, maybe we'll have an plus 1 times 1 over an, just the reciprocal of an. Multiplying an plus 1 and the reciprocal 1 over an, you can see that there's going to be quite a few things that we can probably simplify here. But let's start off by getting rid of that absolute value first. There's a couple things in particular. This negative 1 to the n, and this negative 1 to the n minus 1. Well, you can see that actually most of that's going to cancel out, but we're either going to be stuck with either positive 1 or negative 1. However, the nice thing here is that the absolute value can be applied to each of the individual factors. That's using a property of absolute values. The absolute value of a times b is equal to the absolute value of a times the absolute value of b. And the same thing works with quotients. So if we apply that absolute value to negative 1 to the n, we know that that's just going to equal 1. And the absolute value of negative 1 to the n minus 1, that's just going to equal 1. And every other expression here, n plus 1 to the fifth, 2 to the n, 2 to the n plus 1, and n to the fifth, are all going to be positive because n is starting at 1 and incrementing. So the absolute value only will get rid of negative 1 to the n and replace it with 1, and negative 1 to the n minus 1 and replace that with 1. All of the other expressions will remain exactly the same. That's already simplifying things for us. The only other thing I'll suggest here is maybe to group similar looking factors in the numerator and denominator and split this up into fractions. N plus 1 to the fifth over n to the fifth, they're fairly similar. They're both going to be powers of some expression of n. And 2 to the n and 2 to the n plus 1 are both exponential functions with the base 2. From there, we can start to simplify each of those fractions separately. N plus 1 to the fifth over n to the fifth can be rewritten as a common expression, n plus 1 over n all to the power 5. And then we can take that 2n plus 1 and split the factors there. We'll take one factor of 2 away, and that's the same thing as 2 times 2 to the n. Now you can see that a 2 to the n and a 2 to the n cancel out, and we're left with 1/2. We can also take that rational expression, n plus 1 over n, and split that up into two fractions, n over n plus 1 over n. And that gets us 1 plus 1 over n to the 5 times 1/2. That 1/2 is just a constant multiple, and that can be moved out front of the limit. And using one of our limit laws, we can actually just take the limit as n goes to infinity of 1 plus 1 over n, and then apply the exponent after the limit. And here's applying those limit laws. 1/2 times the limit as n goes to infinity of 1 plus 1 over n all to the fifth. And well, 1 over n gets very small, approaches 0, so that limit is just going to get us 1 to the power 5. That times 1/2 gives us the value from this ratio test. That's just 1/2. Now, going back to the different circumstances, we have 3 conditions here, and we will check and see which of these 3 conditions is true for us. The first hypothesis, well, if the limit as n goes to infinity is equal to some number L, in this case we have 1/2, and if that is less than 1, which is true, then we are absolutely convergent. So we can go ahead and write that down as our conclusion to this series. We can say, by the ratio test, this series is absolutely convergent, and therefore it is also convergent. So you can see right away, the ratio test is super useful when we have powers of n or when we have something that kind of looks a little geometric, something of the form constant a to the power n. It's also very useful when we see factorials though. So let's try another example. In this example, we have a mix of powers or polynomials, n squared, and we have a mix here with a exponential, 3 to the n, but we also have this factorial. So let's just remember what n factorial means. Remember that n factorial is the product of the first n positive integers, 1 times 2 times 3 times 4, and so on, all the way up to n. Or we can write that as n times n minus 1 times n minus 2 times n minus 3 and continue to multiply by the next highest integer until we reach 1. We also have the definition that 0 factorial equals 1. Okay, well, we'll use that in particular when we try to simplify using the ratio test. Once again, for the ratio test, we are given our an. That's the expression in the series, n factorial over n squared times 3 to the n. We can get an expression for an plus 1 by changing all of the n's and replacing them with n plus 1. That will be the next term in the series. Now that gives us n plus 1 factorial. Now similar to the last example, instead of finding the ratio of an plus 1 over an, it might be better to look at the product of an times the reciprocal 1 over an. And multiplying by that reciprocal, hopefully we can start to simplify. You can see we have an n plus 1 factorial in the numerator. We have an n factorial in the denominator. We have an n squared in the numerator and an n plus 1 squared in the denominator. We have a 3n in the numerator and a 3n plus 1 in the denominator. All of these things are fairly similar looking components. We should just match them up and turn this into 3 separate fractions, all being multiplied as one big product. Let's start off with the factorials being our first fraction. N plus 1 factorial over n factorial. Our second fraction, n squared over n plus 1 squared, and our third fraction, 3 to the power n over 3 to the power n plus 1. Now you have to be a little careful here about simplifying that factorial. N plus 1 factorial is a lot like n factorial, except it's just going to start one number higher. N plus 1 factorial is equal to n plus 1 first, times the next highest positive integer, which would be just one less than that. But n plus 1 minus 1 is just n. So that would be the next factor in our factorial. And then 1 less, n minus 1. 1 less than that, n minus 2, and so on, until eventually we would reach 1, the end of the positive integers, and that would be n plus 1 factorial. Now just notice the only difference between n factorial and n plus 1 factorial is the addition of one more factor. So we can actually write this as n plus 1 times n factorial. And that's how we're going to simplify that ratio of n plus 1 factorial over n factorial. Making that little substitution where n plus 1 factorial is equal to n plus 1 times n factorial, you can see some cancellation that we can do there, n factorial and n factorial. And then similar to the last example, we're just going to write n squared over n plus 1 squared as one big fraction all squared, n over n plus 1, and we're going to split that 3 to the power n plus 1 into 3 times 3 to the n. Now we can simplify each of these fractions. The first fraction just reduces to n plus 1. The second fraction we can't really do much with, but knowing a little bit about what we like to do with limits as n goes to infinity, we might want to divide by the highest power of n in the denominator. So n over n is 1, and we have 1 in the numerator, 1 plus 1 over n in the denominator. That whole thing squared, and in our third fraction, we can cancel common factors of 3 to the n and get 1/3. Let's use limit laws now and take a look at the limit of each of these individual factors first, see what those limits are, and then look at the product. Now, we're going to be taking the limit as n goes to infinity. In one of these cases, we have a constant, so that's just 1/3. And we see as n goes to infinity, our middle fraction will approach 1 over 1 plus 0, which is just 1. Both of those limits exist, but this first limit here, unfortunately, as we see that n goes to infinity, n plus 1 gets infinitely large. So overall, this limit does not exist. We say it equals infinity to show that this ratio continues to grow larger and larger. So, what is our conclusion? Well, based off of the second hypothesis of the ratio test, if the limit equals L, which is greater than 1, or if this limit equals infinity, then by the ratio test, this series is divergent. Now, hopefully this gives you a little bit of enlightenment about the nature of polynomials versus exponentials versus factorials. By taking a look here, you see that we've got a polynomial in the denominator. That's growing larger, it's getting infinitely large. But we've seen that polynomials don't grow as large as quickly as the exponential functions do. Well, that's okay. We've got an exponential function, 3 to the n in the denominator. That's getting exponentially large. It's getting so very big for large values of n. So that seems like it could be convergent as well. But not until the factorial comes around. This n factorial in the numerator, that is growing so much larger, so much quicker than even the exponential and polynomial in the denominator that eventually you see that this thing diverges. So it really tells you factorials grow super, super large, not exponentially, but even quicker than exponentially. So wherever you see that factorial, that's going to give you a pretty good kind of guess as to whether or not it's going to converge or diverge. When you see a factorial in the denominator, it's probably convergent, but you need to check using the ratio test. Now, we haven't seen an example yet where the root test might be useful. Like I say, it's a little bit more niche. Let's try an example where you can obviously tell that the root test is going to be useful. Well, in this series, we have a big expression all to the power n. So, it might be a little bit more obvious. Having something with the nth root in our test for convergence is probably going to be the way to go here. Well, in the root test, we only need to look at an. That's the expression that's already given to us. 3n plus 1 over 5n minus 4 all to the power n. And we're going to be taking the absolute value of that first before we take the nth root. So we may have to do a little simplifying before we can cancel nth roots and nth powers. Plugging our expression in to that absolute value, we have the absolute value of 3n plus 1 over 5n minus 4 to the power n first to deal with. Let's just see whether or not we have to do any manipulating in order to simplify that absolute value. Now, n starts at 1. If we plug 1 in on the numerator, 3n plus 1 is positive, and it's going to stay positive as n gets larger. In the denominator, 5n minus 4, when n equals 1, is equal to 1. And it's only going to get larger as n increases. So that's always going to be positive as well. If the numerator and denominator are both positive, then the fraction is positive. And a positive number to any power is still positive, which means that the absolute value of that positive number is just going to be itself. So the absolute value of that expression is equal to the expression itself. We can get rid of that absolute value. And from there, our nth root from this root test and the nth power in our expression for an should cancel each other out. That gives us the limit as n goes to infinity of 3n plus 1 over 5n minus 4. Now, just remember, it's maybe worth noting that the nth root of something to the power n don't always exactly cancel each other out. Remember that if we take something squared and we took a look at the square root, then, well, they don't quite cancel out all the time. For instance, if I take negative 1 and I square it, I get 1, and then I take the square root of 1 and I get positive 1. So it didn't quite cancel out. Negative 1 squared square rooted is positive 1. But that's where this absolute value is handy. It takes all the numbers, makes them positive, so that when we look at the nth root, we get the same value again. So that's where we have that absolute value in this root test. Good news here is that that absolute value didn't do anything. All of our numbers were already positive. So 3n plus 1 over 5n minus 4, that's a fairly simple limit to work with. You can probably guess what it is already. But if you are going to show an explanation as to what this limit is going to equal, we could probably just either use L'Hopital's rule, or we can divide by the highest power of n in the numerator and denominator. Either one works here. Either one works really, really quickly. Here you can see I've divided by the highest power of n in the denominator, and I've got 3 plus 1 over n over 5 minus 4 over n. And 1 over n goes to 0, 4 over n goes to 0, and we're left with 3/5. And much like the same sort of scenarios with the ratio test, you want to know if this limit exists or not. If it does, we want to check and see if it's less than 1, greater than 1, or equal to 1. Worst case scenario, it equals 1, and we don't get a result. Good news here is our limit does exist, and it is less than 1. So our conclusion says, by the root test, this series is absolutely convergent, and therefore it must also be convergent. There we go. That's going to be a couple very useful tests, although we can see that the root test is probably less useful than that ratio test. Ratio test is going to be a very quick default way to go, so long as you see things like polynomials or exponentials, and especially factorials. Sometimes you can just very, very quickly take the ratio of an plus 1 over an and simplify, and then hopefully you get a nice number out of it. If that number is less than 1, boom, it's convergent. If it equals infinity, or does not exist, but gets larger and larger, infinitely large, then it's divergent. Or maybe the limit does exist, it just happens to be bigger than 1, and it's divergent. You're going to have a tough time with that ratio test if the limit equals 1, but you've got other tests and other videos that you can maybe take a look at. Maybe one of those will work. Thanks for watching, and I'll see you in the next video.